Okay. Any questions before I start? So I was thinking what to do for the lab today. So following the general sort of, plan we have had throughout the semester, where we sort of do some lab work based on what we did on Wednesday's class. So today, let's do something about the SIR models again, slightly just to incorporate a few additional elements. So you remember that we had these three equations. S prime is equal to minus alpha beta Si, right? And I prime is equal to alpha beta Si minus gamma r. R prime is equal to gamma r, right? So we wrote this very, very simple SIR model.
Gamma I, sir.
Oh, gamma I. Yeah, thank you. Oh, so I must be small the way I have been writing. Huh? I don't know why it's not erasing. Something, it's like a permanent marker now. Huh? I can't erase it anymore. Somehow magically it went. Is it correct now? Okay, so we had this simple SIR model. We wrote down the assumptions, and there we sort of arrived at this basic reproductive number that was given by alpha beta divided by gamma, right? So what does this mean? We didn't discuss as much on this. This basically tells the following. See, what is gamma? Gamma is the rate at which recovery of the infected individuals is happening. Okay. So whenever you have a rate, if you take the inverse of the rate, you get a time scale. Do you agree with that? So inverse of a rate is a time scale, right? So we can also write R0, therefore, as alpha beta times tau. Okay, so what is alpha beta? We discussed what is alpha beta. Alpha beta is the sort of, infection rate. It's actually per capita infection rate, right? Measured in per capita unit, meaning per individual, per every infected individual, right? So now, what is tau? Tau is the recovery time. So if we take the per capita infection rate and multiply it by how long does it take to recover, what do we get? That's basically the number of new infections, right? Caused by an infected individual, before that person recovers. Is that correct? Which basically means if R0 is 2, so this individual who got infected during the time of being infected and before this person recovers, infects 2 individuals. If it was 3, it's 3 individuals and so on, right? So that's the interpretation of R0. It's the basic, that's why it's also called basic reproduction number. It's a reproduction of the infection, okay? So that's why it's a very useful concept. So keep that in mind. So today what I would like you to do in the lab assignment is the following. Today's assignment is mostly sort of, just to think about adding more complexity and more elements into this kind of a model. Okay, in the first step, add the following, add what's called exposed individuals. What does this mean? So usually what happens is that you have a susceptible population, right? And then there are infected individuals. And what happens is that these guys, because of the interaction, these guys cause an infection to susceptible individuals. So consequently, we have S turn into I, right? Because of the interaction between these two. But usually what happens is that in a large number of cases, the individuals don't become infected immediately. So they are exposed to the virus because of the interaction. Okay. And then after some time, they become infected. So there is some time lag between, in some sense, for a susceptible individual to become infected and also infectious. I hope you understand the difference between having been infected and becoming an infectious person. Okay. So to sort of distinguish that, we add this compartment called exposed. So what I would like you to do is add this compartment and write, incorporate this compartment and write the, new set of equations. Assume that all the rates as before remain the same. Okay. This is gamma. Okay. This will be alpha, beta. Okay. And at some rate, these guys now turn into this, add a new parameter, alpha, beta, gamma, maybe let's call this lambda. Okay. So that's, now we'll have basically now 4 equations. How will the 4 equations look like? S dot, E dot, I dot, and R dot. Okay. And then what will be the R0 for such a system? Is that fine? So here's the first thing I want you to work on. So how do you incorporate these exposed individuals in the system? Okay. That's the first lab assignment. The second one.
So just to clarify, again, the death rate is assumed to be 0. Like no
yes,
death.
let's just assume that to be the case. You can add, it doesn't really make things so dramatically different. So the only thing that will change is the number of individuals who are alive will change with time now. But still S plus E plus I plus R plus D will still be equal to total N you start off with. Okay. Yeah. So let's assume there are no deaths. Okay.
Sir, and one more doubt.
Yeah.
An exposed individual is someone who has caught the pathogen but can't spread it to others, right?
Exactly. That's why we call them exposed individuals.
Okay.
You can I'm going to use exactly same word. Had caught the virus or whatever, but is not infectious, which is why the blue arrow goes only from I to S. Okay. So these class of models are also called SCIR models. Okay.
So,
yeah.
With respect to these exposed individuals, they'll get infected over time, right? But they can still spread infection, right?
So let's assume they don't spread infection in this case. Okay. So they spread infection only when they're in this compartment, I compartment. So everybody in a E will become I. Okay. But when they are in E, they don't infect. Is it clear?
Yes, sir.
Okay, yeah, great. So in some sense, you can intuitively see that it exactly makes not really a whole lot of difference, except that it makes the time scale of reaching from S to I a bit longer, right? Other than that, it doesn't really do anything else in terms of the overall dynamics. You can intuitively sort of see that very easily. Okay. Now, the second thing I want you to do is, consider E as before, plus also the fact that there are different types of infections that can happen. Okay, what do I mean by that? Okay, so you can have okay, now what do I mean by that? So I can have multiple sort of possibilities. You can be mildly infected. You can have a severe infection. Is that fine? And maybe we can also have A, meaning asymptomatic infection. Is that clear? There are three possibilities for I. Okay, and now that we are making this distinction, let us also incorporate depth. Okay, a new compartment. Now, how will this look like? Now, again, there are many ways to model this, but so that we all have a common framework, let's think of this in the following way. You have S becomes E. Okay, E can become one of the three: asymptomatic, mildly symptomatic, okay, and then severe. Is that fine? So let's now consider three different rates: lambda A, lambda M, and lambda S. Is that fine? And then you have now two possibilities of this. One is you can get recovered or you can die. Okay, so let's assume that everybody here goes there. Okay, so let's assume these sort of arrows. Okay, only severe will die, but these need not. Is that fine? Now we need an additional set of symbols. We have used lambda. Do you recommend lambda? Maybe theta. And then we already had a gamma. No, why do we need a theta? No, we don't need a theta. We already had a thing gamma. Okay, and then this is, let's call this delta. Okay, delta. Okay, so I would like you to now write down a set of differential equations for this, and then what is R0 in this model? Okay, so I would like you to do these two things today. Is that fine? Any questions on the second part? Okay, so if there are no questions, we can now start working now. Okay, and,
severe or others.
Sorry,
Like
I only partially heard you.
Like how do we determine that the exposed individual will either have of the three types of infection?
Exposed individual don't have an infection, right? They're
Yeah.
not infectious. They have the infection, but they are not infectious yet. But they become one of them with these three rates: lambda A, lambda M, or lambda S. They go to one of these three. After they become, they turn into one of the three. Is that fine?
Yes.
So I'm not sure whether you mentioned this because I lost audio, but the rate of which each type of infection goes back to like the general, like its capacity to infect others, will that change?
That's a very good point. So, so in the previous instance, we had only one eye compartment, right? So you had, this only one blue arrow. Now, how many blue arrows do you have?
We'll have 3.
We have multiple blue arrows, right? We have one here. We have another one here, right? And another one here. Okay. Now, in fact, we do know from many diseases that, they're not same. Okay. So you can, so beta is a parameter that sort of, determines that. You can assume that they're all different. Is that fine?
Yeah, thank you, sir.
So even alpha will be different, right? The contact rate, for instance.
Yeah, it can be different because you can imagine that you are more likely to avoid contact with, a severe person than with an asymptomatic person, right? So maybe I think, but alpha beta always come together. So there's really no good reason to separate them out. Is that fine?
So we can take like this alpha beta as an
As
infection
a-
rate, which is going to be different for
Exactly.
each of these
Yeah.
cases, right?
Absolutely. You can, in fact, let's do a simple thing. Let's all agree to call alpha is equal to 1 just to make life easy and reduce the number of parameters. You can always get rid of one parameter, right, in our life. So you can just take alpha is equal to 1. Okay. By varying beta, you're achieving the same thing. Is that fine? Although, in more realistic, when you want to really work with real data, you do want to separate them out. But, I think for the purpose of what we're doing today, they don't need to be same. I mean, they can be same. Sorry. Any other questions? Okay, if you do these two things, I will have a third one. So why don't we assemble back at 3:30? Is that fine? So in the meantime, I'll try to visit you all by after 5th. I don't think you, given your experience right now, I have a feeling that we'll finish these two even before that. Okay. So in fact, if you do finish this before, a third thing I would like you to think is that, this is something I was actually hoping to give you myself, but I didn't have time. I wanted to give you a code to simulate. Okay. This kind of, sort of SCIR class of models. But unfortunately, I didn't have time to do that. But I don't know, maybe it's not particularly useful. But I think that this will require some thought and discussion. This question, what is R0? Actually you will need, writing the model itself may not take a lot of time, but what is R0 will take time. So let's not worry about that. Let's not worry about this. Okay. Okay. So and another point is, I was thinking that there's we have only Wednesday's class next week. I can use that basically for answering any questions you have. So I don't plan to cover any new topics or anything. So Wednesday's class will be mostly for answering any questions and doubts you may have about any of the classes so far. Okay. Or maybe to sort of, even summarize what we have learned, sort of, just stepping back and see what all have we learned, what all have we not learned. Okay. That's what we will use mostly Wednesday's class for. But today, I think, these two will be sufficient, and think more about R0. Okay. That's all for today.
So what about Friday 28th?
I thought that the semester ends on 27th. Isn't that right?
We were told 28th.
I think it's 28th.
Okay. Actually, if it is on 20th, I had one plan. I thought it's actually on Thursday, or actually Wednesday, which is why I thought there was no point because I will not be able to do a lab, because I wanted to do one more interesting application of, what we have learned using real data as an example. So if next week is available, I think it might be interesting to cover. Yeah. So, if you're sure that it is actually 28, we can do that. Is that fine?
Yes, sir. At least like in
Yes,
our
sir.
other courses, we're taking classes on 28. So
So actually that would be great then. Yeah, that's something I know I would really like to. I really wanted to, but maybe I misread the email. It actually will be really good. I wanted to cover one more sort of application of what we have learned. Okay. Okay, cool then. Then I will do that application. I'll sort of try to summarize some papers and so on. And what I can also try to do is I'll also try to sort of give you some sort of advice on how do you, for example, if you now want to read a paper, right? Let's say in theoretical ecology, or how do you go about reading those kind of papers? Maybe I can also discuss those kind of issues, which are sort of not covered in a standard way in books. Is that fine? Okay, that sounds good then. Okay, so for now, let's just stick to these two simple goals today. Okay, and I will visit you all as we go through the class. Do you need to see this more?
Sir, I had one question.
Yeah.
With respect to like this severely infected population, like can't we take that like to a death map directly? Like instead of, because anyways, like mild can be ranging from asymptomatic to severe, right? So severity could be indicated by death, right?
So you're saying that, yeah, I mean, you're right. You can say that severe will basically lead to death all the time, right? That's what you are saying, no?
Exactly, and that's how I would define
yeah.
the severity instead
Yeah.
of taking another arrow from IS to R.
IS to R is not possible. I think some of these become, I will tell you why some of these are actually useful. For example, if you need to, for example, just in the context of the current disease COVID itself, as we know, asymptomatic people basically require no treatment at all, right? Whereas mildly infected people require some treatment, right? And in fact, if you look at, for example, models of COVID-19, for example, they also have a compartment called hospitalized. Okay. The reason why people sort of add more compartments is if you want to have a realistic, some reasonable projection of how these numbers, okay, are going to change over time. And if you want to tell, let's say, a policy maker, hey, look, these are the projected numbers under hospitalized category, those who will surely require hospitalization, right? And even among hospitalization, not everybody will require an ICU, for example, right? So if you want to actually get some reasonable estimates of all of these different levels of treatment that you need to provide to people as a function of time, it is useful to have these kind of compartments. But from a purely mathematical sort of principle point of view, you actually don't need, and you're absolutely right about that, because we can sort of merge many of them to sort of, treat them as effective parameters. You don't actually need to separate as many.
sir, but won't the recovery rates change? So it'll be like an unfair approximation that you would be doing. Because if you remove IS category entirely, then in reality, your RM will become some function of the original RM and RS, right?
Yeah, so it will, of course, you're right. You see, any approximation you make is an approximation by definition, right? Which means it is going to miss out something that was happening. So the question really one must ask is, how important that approximation we are making is. So, so what's the purpose of your model becomes a very important parameter there. So there is no one answer to these questions. For example, should you add one more, that distinguishes even severe can have, somebody who needs only oxygen support, whereas there are some other proportion who will need, ICU support also, right? So, you can even, so whether you want to distinguish the two or not, and so on. So all those depends on actually what is the purpose of your modeling exercise. If you wanted to, the idea is to give more and more realistic estimates that people want to use, then you do want to have more. But then it also comes at the cost of over parameterization. Do you really have data to know all the parameter values? Are there sort of previous studies that tell you what the reasonable parameters are? Right? that also then becomes an important issue. Okay. So so that's it from my side before you start now. Any other questions? So we will have the class regularly next week then. Okay. Okay, so I will open the breakout rooms now.